Welcome to Ask and Learn.
This is an interesting problem in that you can solve it using some kind of intuition, but I always tell people to avoid that because a lot of times your intuition is not correct. Um, so what we're asked to do now is figure out what the minimum load is or force is we need to apply here to get this wheel over this barrier, which means that we don't know this angle. So what we can do, again, I'm going to use this as my origin, and there's no force here because just as the wheel is about to lift up over, this force is going to go to 0. We know that, or we can try we can figure out that this at that point that this force is going to act along the basically towards the center of the circle. In fact, over here it also does. But so we know that, okay, so we can use that, and we know where it acts. Okay, so this unit vector I called 2 to 3, since this was 0.2 and this was 0.3. And so our weight we have acting. And then we have two components of P. So instead of doing a magnitude and direction, I just use two components. It just makes it a little easier since we don't have to have sines and cosines floating around. And then we know again that it always acts through this point here, no matter what direction it's applied in. So if you use force and moment balances, it looks like you get 3 equations and 3 unknowns. You think you might get 3 equations and 3 unknowns, but in fact one of those is two of them are the same. 2 of them are actually redundant. So you can't solve for all 3 of these unknowns. But we know that we want to make this a minimum, so we have kind of another constraint on the system. So what we can do is we can get these two forces, these two components, in terms of F and W. So it turns out that Px is minus 0.553F and Py is minus 0.833F plus W. So we know those two things. And now we can get the magnitude of P. Okay, so that's just, and we get the magnitude of P as a function of, let's see here, as a function of F. I should put this F in here. So we plot the magnitude of P as a function of F. Again, we know the weight. And if we do that, what we see is we get this kind of parabolic looking curve here. It's not a parabola, but it's kind of looks like one. And what we see is that, more importantly, is it has a minimum. And we can see that we can figure out the F, the magnitude of this force, when that minimum occurs. And then we can plug that in and figure out that we have to get that the minimum force is 271 newtons, which is obviously less than 272 newtons, but fairly close. So our 30-degree angle, which we could also find because is fairly close to what what we had in this problem here. So that's fairly close to optimal, the 30 degrees. And one other check you can do is you can see that if F goes to 0, then the magnitude of this just goes to W, because if you're pulling, if F goes to 0, if F goes to 0, basically you're just pulling straight up. And so that would be basically just lifting with all of your, lifting the entire weight of this wheel, which would be 50 times G. But instead, you can, instead of 100 at 500 newtons, you can use 271 newtons by using this kind of as a lever arm.